Good morning. My name is Amber Prajapati and I am the co-author of this research paper, Simulating Distributed Wireless Sensor Networks for AGI. I would like to mention and thank my co-author Dr. Bonnie Banerjee, who contributed also towards research and writing of this paper. We started with the aim of finding out if the nodes at the edge of the network are capable of processing complex artificial intelligence or machine learning algorithms. Can they make uninterrupted autonomous decisions in real time, and can they produce actionable insights? So for this we wanted to perform simulations, and we needed a good simulator that can help us basically trigger all the scenarios that we needed. So we started out with these popular simulators: Omnet++, Castelia, NS3, MATLAB Simulink, Contiki, NG-CUSA. And after comparison, we found that Contiki NG-CUSA was a clear winner because it was capable of performing event-driven communications. It provided a lot of supported protocols, propagation models, and the code that was used in simulation was actually directly portable onto the hardware of the sensors, and it was actually open source with substantial industrial and development support, and it supported the simulation on a larger number of nodes as compared to the other simulators that we picked for our study. So we took basically two distinct scenarios for simulations. One was where the edge device itself was doing the complete processing. We are calling this as WSN with no central node in this research. And the other scenario where the edge device is near a central server that does or that helps in processing, and we are calling this as WSN with central node. So here I'm showing WSN without a central node, and actually we use the IEEE 802.15.4 standard as the underlying technology for simulating the WSN with no central node. And here I'm showing uh, how it maps internally inside the network layer of Contiki NG. So on the left hand side I'm showing the popular OSI model. A special mention needs to be done for the data link layer, which is basically composed of two different sublayers, LLC and MAC layer. And the MAC sublayer actually in Contiki NG is made up of two different layers. One is the MAC layer and the other is the RDC layer. And the RDC layer, we utilize this IEEE 802.15.4 standard, which is a very powerful standard for basically multimedia processing even on the nodes. The other scenario was WSN with the root node, and we utilized a very successful 6LoWPAN protocol called as routing protocol for low power and lossy networks, RPL. And here I am showing in the diagram the green node is the central node, and the remaining nodes are the client nodes. So the radio propagation models that I talked about, we basically picked two models which were closer to real-time scenarios. Here I am showing unit disk graph medium UDGM distance loss radio propagation model. So it actually models two different circular disks around a node. The inner one is where there is a complete reception. I'm showing this here as a green. Basically Contiki shows it as green, and there is a gray circle around it, which is a circle of interference where the packets are actually interfered by the packets from the other nodes, so the reception is not fully guaranteed and is not fully clear. And beyond these two circular disks, there is actually no reception. The other propagation model we used was a multipath ray tracer medium MRM radio propagation model, which is a highly capable propagation model which can model the obstacles, and it uses the ray tracing technique to trace the radio receptions. So here this diagram is showing that there is an obstacle, and the red circle that you see here is actually where there is no radio reception. So let's talk about the algorithms. So the algorithms were actually very simple. They were actually intended to prove that the node, which is simultaneously a sender as well as a receiver, so when it is sending certain message, it is capable of performing, a conditional logic, and based on that logic it can detect basically what nodes it is supposed to talk to, which is like for targeted communication. and after all that processing it is able to connect to that target node and communicate well. And while receiving, when the same node is working as a receiver, it actually randomly receives whenever there is a packet coming to it, and processes that packet and sends a confirmation back. Here, one thing to mention is that the detection of the nodes around a node is actually done by MAC address, by finding the MAC addresses, because here we are using IEEE 802.15.4 channel. The other algorithm is exactly similar, but it uses the RPL protocol, and it actually does basically performs the neighbor discovery based on routing table. Rest of the things are same, that each node has to first of all check the conditions, then find the node, and then do the processing, and send a targeted communication to the intended node. And it also acts as a receiver, where it can receive the callback event, send the confirmation or the acknowledgement of the message received. So having done all that, basically what we did, we used two propagation models which were closer to real-time scenarios. We picked two scenarios which were again closer to real-time scenarios, like one having one without using a central node, one using a central node. And then with this with those algorithms, we were actually trying to say that each node is capable of performing complex logic, conditional logic. It can detect the node, it can do the processing, and it can send uh, the message back to to a particular node, which it intends to send a message after performing all that logic. So the results that we found after all this, uh, after running the code on the sensor nodes, that the network throughput in the UDGM RPL WSN with a root node had a lower network throughput, whereas the MRM WSN without root node had a higher network throughput. The radio duty cycle, which represents the network lifetime, we found that for UDGM model, the RPL WSN with the root node had a lower network lifetime, whereas for MRM model, the RPN WSN with a root node had a lower network lifetime, as we are showing in this figure. The power consumption, we found that for MRM model, the WSN without root node has slightly higher total power consumption because of higher CPU and higher transmission power consumptions. And the UDGM model, uh, the RPL WSN with the root node, we found that it consumes more power. The packet delivery ratio for UDGM model, the RPL WSN with the root node had a degraded PDR for the 4 child nodes, and obstacles and larger distances among the nodes, they negatively impacted PDR in both types of WSNs. So how does that fit Edge AI? So we demonstrated that asynchronous event triggered communication can be performed because the nodes are capable of sending packets based on conditional logic, which was implemented in the source code of the emulated nodes in ContikyOS Koja. We demonstrated that the nodes perform targeted communication because the nodes are sending packets to specific recipient nodes using ContikyMac or RPL protocols from the network stack of the ContikyOS. And we demonstrated that the nodes were performing dynamic communication, as the nodes were able to detect the target nodes using ContikyMac carrier sensing and RPL routing mechanism. Uh, we hope that this study will help ascertaining the benefits that the edge nodes can perform complex processing. They are capable of performing autonomous processing, and they can produce actionable insights. Thank you.